On a wet road, reflected light can turn the view white. Rotate a pair of polarized sunglasses, and much of the glare fades. In our lab, the same turn sends a detector from bright to almost dark. The filter still looks clear. So what is it choosing? Not a color, not a place. A direction. To understand how a clear filter can choose a direction inside light, we need a kind of number that carries direction. A vector. Some measurements need only an amount. 22 degrees, 80% brightness, 5 meters per second. These are scalars. Now the detector trolley must move 5 meters. That instruction is unfinished. 5 meters which way? 5 meters east gives both size and direction. That is a vector. Think of a vector as a change instruction, how much and which way. We draw it as an arrow. Its length shows magnitude. Its arrowhead shows direction. Slide the arrow somewhere else without turning or stretching it, and it still represents the same free vector. Put the lab floor on a coordinate grid. Start at the origin. Move 4 squares right, then 3 squares up. The diagonal arrow is vector A, with components 4 and 3. Those two numbers describe one move. Its length is 5, because 4 squared plus 3 squared equals 5 squared. One subtle distinction. The point 4, 3 names a location. The vector 4, 3 names a displacement. When the vector starts at the origin, they share an endpoint, but one is a place and the other is an instruction. Shift the vector to another tail. Same length, same direction, same vector. Our detector trolley needs 2 corrections. First, vector A moves 4 right and 1 up. From its new position, vector B moves 1 left and 2 up. Place the tail of B at the head of A. The one move from the first start to the final finish is a plus B, 3 right and 3 up. We add components because horizontal effects combine with horizontal, and vertical effects combine with vertical. Reverse the order and we still reach the same endpoint. Head-to-tail motion and the parallelogram tell the same story. Addition combines effects. Soon we will run that picture backward and split one light vector into 2 pieces that add back to the original. Now lift the camera and add a z-axis. A vector with components 4, 3, and 2 means 4 along x, 3 along y, and 2 along z. 3 dimensions are not a new species of vector. There is simply one more component. That matters for light. Its electric and magnetic fields point sideways while the beam travels in a third direction. Addition asks, what is the total effect? The dot product asks a different question. How much does one vector line up with another? Keep vector A fixed and rotate vector B. Point the same way. The result is positive and largest. Turn to 90 degrees. There is no alignment, so the result is 0. Point opposite, the result is negative. The rule is a dot B equals the length of A times the length of B times cosine theta. In coordinates, multiply matching components and add. Crucially, the dot product is one number, a scalar. It reports alignment. It does not itself point anywhere. Choose a direction p hat that is exactly 1 unit long. The dot product a dot p hat is the signed amount of A along that axis. Call that scalar c. Now multiply c by p hat. The result is an arrow along the axis, the projection vector. Keep the distinction sharp. The dot product c is a scalar. The projection c p hat is a vector. The remaining perpendicular arrow, added to the projection, reconstructs A. This decomposition is the key to the light filter. A window blind is a useful first picture. It favors one orientation and rejects another. A real polarizing filter is not literally made of tiny slats, but directional selection is the right intuition. Now follow the light itself. The cyan wave profile curve connects the tips of electric field arrows. It is not the path of a particle. As the pattern advances, each field vector grows, shrinks, and reverses sideways while the light travels forward. We slow this motion enormously so you can see it. Before the first filter, the source offers field directions in more than one orientation. The first polarizer prepares a diagonal input field, E in. Look between the filters. the wave has not vanished. Every visible field arrow now oscillates on that same diagonal line. The second filter has a unit transmission axis, p hat. Freeze 1 instant. The marked angle theta lies between E in and p hat. First, use vector addition. The parallel piece plus the perpendicular piece reconstructs E in head to tail. Next, the dot product computes E in dot p hat. That result is the scalar amount C aligned with the filter axis. Projection then multiplies C by p hat, producing the transmitted vector E out. The perpendicular component ends at an ideal filter. It does not emerge on the far side. So addition explains the split, the dot product measures alignment, and projection creates the field that passes. With aligned axes, E out keeps the full amplitude. At 45 degrees, the passed amplitude is 1 over square root 2 of the original. The detector does not report field amplitude directly. It reports intensity, proportional to amplitude squared, so the reading is 1/2. At 90 degrees, C is 0, E out has 0 length, the outgoing wave disappears, and the detector is dark. This is Malus law, I equals I0 times cosine squared theta. The cross product solves a different problem. It does not choose what passes. In the next three-dimensional reveal, E cross B will identify the direction light energy travels. Polarized sunglasses use the projection idea. Glare from flat surfaces is often mostly horizontal, so the lens removes much of that component. Now one short trip into 3 dimensions. For vectors A and B in ordinary 3-dimensional space, across B points perpendicular to both. Its magnitude is the length of A times the length of B times sine theta. That is the area of the parallelogram they span. Parallel vectors make 0 area. Perpendicular vectors make the largest area for their lengths. To choose between the 2 possible perpendicular directions, use your right hand. Index finger along the first vector, middle finger toward the second, and thumb points along across B. Swap the order, and the direction flips. Freeze an ideal light wave. Put E along X and B along Y. Then E cross B points along Z, the direction the light energy travels. Half a cycle later, E and B both reverse, but their cross product still points forward. Test the model. Rotate the analyzer to 60 degrees. Before calculating, will the detector read more or less than half? The projected field amplitude is cosine 60 degrees, 1/2 of the original. The detector intensity squares that amount. 1/2 squared is 1/4. Now read the whole experiment. Coordinates place the detector. Addition combined moves. The dot product measured alignment. Projection produced the transmitted field vector. The detector turned field amplitude into scalar intensity. The cross product organized the fields and the direction of energy flow. Projection will return later in quantum measurement. But we need a careful boundary. Today, displacement and electric field arrows live in ordinary physical space. A quantum state vector generally lives in a different, often complex mathematical space. An arrow diagram is not automatically a quantum state, and measurement needs its own rules. We will build that separately. For now, scalars say how much, vectors say how much and which way, addition combines, the dot product measures alignment, projection extracts a directional part, the cross product finds a perpendicular direction. And that is why turning a clear filter can make light disappear.